All right, so my talk tonight was going to be mostly, or it's going to be on the Ice Age floods for the Pacific Northwest. There were actually three different sources. Most of you are probably familiar with glacial Lake Missoula, which is the most common and the most notable source for these Ice Age floods. But a lot of people don't know there were actually two other sources for Ice Age floods in the Northwest. And those two other sources were Lake Bonneville down here in northern Utah. That was a big lake. It was a much bigger lake compared to what it is today. Today, this is the modern Great Salt Lake down here. But during the Ice Age, the Bonneville Basin was filled with water for many hundreds, maybe even 1,000 feet or more deep in the Bonneville Basin. And around 18,000 years ago, there was so much water draining into this basin, had no place to go, couldn't go out anyway. There weren't any rivers draining that basin. So as soon as it got to an opening that it could pass through, a low pass around the margin of the basin, that water spilled over. And that happened at a place called Red Rock Pass. Lake Bonneville got so deep that the water spilled over, and it lowered the level of Lake Bonneville about 300 feet before it hit the bedrock underneath that pass. And that, when it hit the bedrock, then that flood stopped. But for at least maybe 2 or 3 weeks, there was water draining out of Lake Bonneville down into the Snake River, and it went all the way out down through Hills Canyon, through the Tri-Cities, and then the natural path was all the way down the Columbia River, eventually out to the Pacific Ocean. That only happened once about 18,000 years ago. There was another source of floods or flood. It was a single flood, like Bonneville. There was one flood at the very end of the Ice Age from glacial Lake Columbia. And that happened when the Okanagan lobe, which is this lobe of ice coming down from the Cordilleran ice sheet, blocked the Columbia River for through most of the Ice Age. But then at the very end of the Ice Age, as that ice lobe was retreating, that lake was able to break through the lobe of ice and then drain down the Columbia River, going through Wenatchee. And that was just one flood. But then we know the glacial Lake Missoula was the source of many floods. It's as many as maybe 80 to 100 floods during the last Ice Age, between about 16 and 20,000 years ago. We think there may have been as many as 100 separate floods from glacial Lake Missoula. The book that I'm going to be talking about later, I talk about all three sources of the floods, and I present evidence for those in the book. But tonight, I'm going to focus on glacial Lake Columbia, just because that is the focus for most of the floods. And plus, I have a limited amount of time, and I'd rather focus on this flood because it really produced the most spectacular evidence for these Ice Age floods. So the rest of the talk will focus on glacial Lake Missoula. So here's what it looked like during the Ice Age. Today, there wasn't any ice in the northern Washington, Idaho, Montana, but during the Ice Age, Cordilleran ice sheet came down from British Columbia, came down the Purcell Trench down to near the area of Sandpoint, Idaho, and it blocked the Clark Fork River. This is the Clark Fork River Valley here, and when that happened, it plugged the valley so that the water from water draining into the Clark Fork River Valley had no place to go. So it backed up and created this huge lake, glacial Lake Missoula, which was up to 2,000 feet deep here at the ice dam. During the Ice Age also, there was this other lobe, the Okanagan lobe, which I mentioned previously, came down and blocked the Columbia River near Grand Coulee Dam, and it created this other lake called glacial Lake Columbia. But that Lake Columbia persisted through most of the Missoula floods. As Missoula floods came out, it encountered the glacial Lake Columbia, which was already there. And it didn't take much more water from Lake Missoula to drain out or drain into Lake Columbia and then spill over across what we call the Channel Scablands. So there's the ice dam. It was up to 30 miles long from near the Idaho-Montana border all the way down to the mouth, the lower end of Lake Monterey is where the ice dam used to be. So that was about 30-mile long ice dam, and it prevented all that water from Lake Missoula to drain out until the very end, or until the lake got so deep that it destabilized the ice dam and allowed the ice dam to break apart. And all that water from Lake Missoula was able to drain out. That happened in just a matter of 2 or 3 days. Lake Missoula drained, spilled out across the Channel Scabland, and then it all drained down into and through Wallula Gap, which is this very narrow opening, only 2 miles wide down here in the Lower Sound Hills. There was twice as much water going in the gap that could actually go through at once. So the water backed up and created a big lake called Lake Lewis behind Wallula Gap. And then eventually, within 3 weeks, all that water from Lake Missoula was able to drain out through Wallula Gap, down the Columbia Gorge, out to the Portland, Vancouver Basin, and to the Pacific Ocean beyond that, which isn't shown, but it's over here on to the west. We know the last flood was about 15,000 years ago from glacial Lake Missoula, but we do have evidence for older floods going back as far as 1 to 2 million years, which was the beginning of the Ice Age. So there's a long list of flood features or features that are diagnostic, landforms that are diagnostic of these Ice Age floods. And we've divided them up into erosional landforms and depositional. Okay, erosional is where the floods have eroded and worn away the land surface. Depositional is places where the floods were able to slow down, sometimes temporarily, and cause deposition of sand and gravel, creating big giant flood bars, giant current ripples, and slackwater rhythmites down in backflooded basins like in the Walla Walla, the Yakima valleys, where we see these rhythmites, where the floodwaters were allowed to slow way down. And then we have these ice rafted erratics too, which I'll be showing you lots of pictures of. These are rafted erratics that were brought in on icebergs that floated in with the floodwaters from Lake Missoula. The Ice Age floods, Missoula floods, were the brainchild of this one man, J. Harlan Bretz. Actually, Bretz didn't call them the Missoula floods because he really didn't have a source for the floods. During most of his career, he focused on just looking at the evidence for the floods and not really being able to identify the source of the floods. And it wasn't until years later that J.T. Bardee and others introduced evidence for Lake Missoula as the source. But early in his career, about 100 years ago, he was out traveling across eastern Washington within the Channel Scabland and looking at all these unusual landforms that he couldn't explain. And so he started coming over here and doing his field work. And it took a few years before he was able to come out with a conclusion for what he was observing. So in 1923, he introduced an outrageous hypothesis, and that was that the only genetic interpretation yet proposed, which is inherently harmonious and which fits all the known facts, is that of a great flood of water. So this was his ideas early in the 1920s, and he stuck with his ideas for years and years, despite most of the other geologists, his contemporaries, refused to accept his theory because it smacked too much of the Bible, and geologists at the time believed in uniformitarianism, which is the earth changes over a very slow period of time. And if you introduce a theory where there's catastrophism involved, like a Noah's flood, then you're moving too far away from geology. But it didn't take long uh, until the 1950s and 1960s before, especially after other geologists and other scientists started getting up in the air and looking down uh, at this on the scabland, that his ideas actually started to make sense to a lot of geologists. And finally, in 1979, when Pretz was 97 years old, I think, he was awarded the Penrose Medal, which is the highest honor you can earn as a geologist. And his only regret was that he had outlived all his critics who had argued with him for all those decades. But now we all know that Pretz was actually absolutely right, and we honor him for that. So today, this is a Landsat image taken from space in 1972, and on that photo, this satellite photo, you can clearly see the channels that were left behind by the Ice Age floods. Naturally, what was here before the floods is this, where the dark lines are today, used to all look like this light brown and green color down here. That was once covering this whole area of Eastern Washington. It was covered with this windblown soil called loess, which is great for growing crops in this area. But when the floods started coming through, they started eroding down through that cover of windblown soil until they got down into the basalt bedrock. That's a dark volcanic rock that's underneath the Palouse soil, and you can really see the contrast between the loess soil here and where the floods eroded down into the dark basalt bedrock. So it's really clear from space that there was major flooding going on through Eastern Washington, and not just not flooding in one place, but all flooding that was probably occurring simultaneously across this whole entire area. But as early as 1923, Bretz had already figured that out. He, in his travels around Eastern Washington, he was able to actually map the locations of where these flood channels are and where there were sedimentary deposits laid down from the floods. So as early as 1923, Bretz had already figured that out. And the amazing thing is he did it all from the ground. He never got up in the air to see what we can see from space today. He figured this all out just by driving and hiking around the scabland. So I'm going to be presenting pictures now and lots of video clips of these features, flood features, which are best seen from the air. So I have a drone I've used for the last half dozen years, collecting pictures and video of a lot of these flood features that I listed previously and that Brett's discovered. I'll be showing you these from the air, starting with the area of Lake Missoula, starting with the source for the floods. And then I'll be going down into where the ice dam is today and showing you images of what it looks like today and the evidence for the ice dam being there. And then from there, I'll present evidence going downstream into Lake Columbia and then out onto the Channel Scabland. And then from there, I'll show the Wallula Gap where all the floodwaters drained down through the Columbia River into the Columbia River Gorge, and then eventually out to the Portland, Vancouver Basin and out to sea. So I'll be going in chronological order basically, and in the direction the floods were moving in the following images. Okay, so the best evidence, or some of the best evidence for glacial Lake Missoula are these strand lines, okay? You can see these parallel lines that are etched into the hillside of Mount Jumbo. This is just above the city of Missoula. And you can trace them very very easily, going across at the same elevation, one after another. They don't connect. They're all, each one has a discrete shoreline of glacial Lake Missoula, where it once existed. It's obviously not there anymore. Lake Missoula is down here. It's 1,500 feet below the top of Mount Jumbo. You can see these strand lines that go all the way up to this point here. This is 4,200 feet elevation. So that tells you that the deepest point of the lake. And then after that, as the subsequent floods were tended to be smaller than the older floods. So as the lake got smaller and smaller over time, it etched in these strand lines, which were lower and lower. So there's the maximum level of glacial Lake Missoula. It was up to 2,000 feet deep near the ice dam. Here in Missoula, I think it was about 1,500 feet deep. And you can see the strand lines. They just continue on all the way across Mount Sentinel. And then another really good piece of evidence for the Lake Missoula draining very quickly are these giant current ripples, okay? And when the ice dam failed down in the panhandle of Idaho, all that water from Lake Missoula was racing to the void left behind by the ice that was destroyed. And so all the water from Lake Missoula was racing to the west. And in this particular area of Camas Prairie, the easiest way for the water to get to northern Idaho was to go through these passes, these low passes you can see here. During Lake Missoula time, the top of the lake was over, I think it was 400 feet over the top of this knob that you can see here. So everything in this image, except these hills off in the distance, were all under hundreds of feet of floodwater. So imagine a lake still overtopping this mound here, was all racing through it, and it took the path of least resistance, and that was to go through these passes, these lower passes in between this higher knob was a natural place for these floodwaters to drain. You can actually see by the orientation of the ripples that these ripples, the ripples are oriented at right angles to the flow of the water. And you can see these ripples started up here and they went down in this direction. And from this pass, you can see the ripples started up here and they were coming in from the right side up here. And right here along the highway is what is near where the two surges of floodwater merged together. But they were all moving simultaneously, all in the same direction towards northern Idaho. Oops. Do that again, sorry. So here we are, Camas Prairie. And again, this is the Markle Pass. And this is called Wills Creek Pass over here. But during these Ice Age floods, the water was way up here above the highest points, and it was all draining through. As the lake lowered, that water would probably move faster and faster through Markle Pass. You can trace these ripples; they go all the way up to the Markle Pass, and then that's where they stop. Here's a good example of what the interior of one of these bars, these ripples, looks like. This is the debris that was transported by the Missoula floods as they were draining Lake Missoula and creating these giant current ripples. So these ripples are composed of very coarse sand and gravel. Some of these boulders you can see in here are the size of small vehicles, Volkswagens, possibly. So the water was moving very fast, energetically, in order to be able to transport these boulders of that size. So here we are, we're flying up towards the Markle Pass. Here's a beautiful expansion bar that formed as the floods were coming through the gap. They widened, they spread out, and they deposited this beautiful expansion bar, delta bar. This is Markle Pass looking down into Camas Prairie down here in the opposite direction. You can see there's no sediment, there are no ripples up here. It's actually a place where the floods were scouring, and they created these channels, deep channels into the basalt, not basalt, but the bedrock, which happens to be belt rock that I'll be talking about later. So the floods were eroding through the passes because of the higher energy of the floods, and then as the floods expanded into the Camas Prairie, and they deposited a lot of the material they carved out of Markle Pass and the other passes. Here's another feature of glacial Lake Missoula. It's called an eddy bar, and it's a pile of sand deposition, sand and gravel that was deposited by the floods. This is the Flathead River in Montana, and as the floods were escaping and running down the Flathead River Valley towards northern Idaho, the floods would swirl around these tributary valleys on the sides of the valley. And as they swirled around, there'd be eddies that forming of these floodwaters, and they would deposit sand and gravel up onto these bars. So the floodwaters were at least this high, and they probably went up much higher, way up, above here as they were draining out of Lake Missoula a bit. As they went by this tributary valley, they swirled around and allowed deposition to take place. Closer up view of the bar. It actually slopes, it's higher here and it slopes down in the area behind, which is an indication that the deposits were coming from the valley and not from the upper part of the stream. Okay, so the next thing I'm going to show you is Eddy Narrows. And Eddy Narrows was still within Glacial Lake Missoula, but it's a very narrow valley where most of the water upstream in Lake Missoula, or all of the water upstream in Lake Missoula, had to drain through this pass on its way to the ice dam that was destroyed by these floods. So the significance of Eddy Narrows is it's a very narrow canyon, and it's a single canyon where all the floodwater had to go through. There are other canyons downstream and upstream where there are multiple canyons that were draining at the same time. But in this instance, there was just a single canyon. So it was very easy for J.T. Bardy and others to calculate the volume and speed and the duration of the floods that were passing through Eddy Narrows. So that's the significance of Eddy Narrows. And it's, as you can see coming up, it's a very narrow gorge through the gap of Eddy Narrows. During the Missoula floods, Lake Missoula was up close to the tops of these hillsides on either side. So this was all underwater. And as Lake Missoula drained, all that water from upstream had to go through Eddy Narrows on its way downstream. Bardy estimated, I think he estimated about 20 million cubic meters per second of water was moving through Eddy Narrows during the largest flood. And it took about 3 days for the water to drain based on the volume of Lake Missoula that he knew of behind the ice dam. So here's I like this image produced by Dave Bennett, who was a pilot up in the Missoula area. Yeah, he took this picture flying in an airplane, and then he gave it to a person that's an expert at computer graphics, and this person put in where he thought the ice dam was. This is close, very close to where the ice dam was. They moved up the Clark Fork River Valley from the area of Lake Pend Oreille, and then Lake Missoula that formed behind the ice dam, which was about 2,000 feet deep here behind the ice dam. There goes my cat. Oops. Sorry about that. Let's see if I can get back to where we were. Okay. So the Clark Fork, this valley now today is filled by the Clark Fork River, or is occupied by the Clark Fork River. But during the Ice Age, the Purcell Trench lobe moved up the Clark Fork this far before it terminated against the edge of glacial Lake Missoula. But today, the Clark Fork River is 2,000 feet below the level of where glacial Lake Missoula used to be. And you can see there's lots of icebergs floating around, probably lots of boulders and things embedded in those icebergs that we'll talk about later. So I mentioned earlier there was most of the rock near the ice dam is composed of this belt rock pelt supergroup that's 1.5 billion years old. The very old rocks, they're metasedimentary rocks that have been metamorphosed and become very hard. They're very resistant to weathering, chemical and physical weathering. So you actually you see them quite a bit as erratics that were rafted in on icebergs that floated downstream after one of these ice age floods. And here you can see there's a beautiful quarry that they're removing all this type of rock. These are the wall of this wall is made up of these big boulders of argillite, mostly argillite and quartzite, which we can see downstream. And I'll be showing you examples of these in subsequent slides. Today they use it for a lot of decoration. So in the Telford area, a few miles east of Grand Coulee, here's a beautiful piece of argillite. Here's another big chunk of argillite in the Tri-Cities area where I live. And then we see these boulders of belt rock all the way down into the Willamette Valley. And this is looking north with the Willamette Valley over here, the Coast Range of Oregon here. And you can see up on one of these knolls, higher knolls in the foothills of the Coast Range, you can see there's a beautiful boulder, big boulder of argillite. Metasedimentary rock that used to one time was shale, just has been metamorphosed into a very hard argillite. This is an image that Stevo Minsky produced showing you how the boulder might have looked after it was rafted in and the Lake Missoula floodwaters drained out. This is what it looks like today. There's actually a trail you can follow. It's a state park, has a trail that you can actually hike about a quarter mile up from the main road up to this beautiful piece of argillite. Okay, so now we're back at the ice dam for glacial Lake Missoula. This is the Clark Fork River. And you can see it's draining down into Lake Pend Oreille, which is up here. But during the Ice Age, during the Missoula floods, this whole area was all filled with ice, 3,000 feet of glacial ice that was approaching the tops of these hills, these higher hills on either side of the valley. So this was part of the ice dam for Lake Missoula. Here's where the Clark Fork River drains into Lake Pend Oreille. This is the lower end of the ice dam. At the lower end of Lake Pend Oreille near the little town of Bayview. And this is where the ice, this is as far as the ice got, the ice dam. This is the same image, kind of taken from the same perspective. Here's Cape Horn Peak is over here. And you can see there's this other side of the valley. These arrows point to the common points in both images, but you can see during the Ice Age, the Purcell Trench low came all the way down here. Lake Pend Oreille didn't exist back then because it was filled with many thousands of feet of ice. But today we have beautiful Lake Pend Oreille, the town of Bayview here, and Rathdrum, Farragut State Park over here in this point of land. So very different today than back in the Ice Age. So here's kind of a pan starting with Cape Horn Peak, Lake Pend Oreille. Here's that point of land that sticks out into Lake Pend Oreille where Farragut State Park is located. You can see, oops. Okay. All right. We'll repeat here. There's so many buttons on these PowerPoint slides, it's hard to always get the right, push the right button. So I apologize for skipping around here. So here's where we were talking about Lake Pend Oreille, Farragut State Park. And okay, I'm just not going to mess with the buttons right now. I'm just going to let it play through. So the ice came very close to the very top of the Cape Horn Peak, and it was sitting up here. It was grinding up against this hillside here. You can see where the glacial ice actually beveled this slope, this planar surface that you see here. This is the Rathdrum Prairie out here. That's the outburst plain that was deposited by these floodwaters that were escaping out of the ice dam. This is the very lower end of Lake Pend Oreille. And there you can see that beveled slope where the ice was sitting during the last ice age. Okay, so we were just looking at this area here where Lake Pend Oreille is today. This was all part of the ice slope and went all the way up to the Idaho-Montana border. And when that ice dam broke apart and Lake Missoula waters were allowed to drain out, they flowed down through this opening here, and then they spread out into the Rathdrum Prairie. And here they were confined, so the water moved very quickly, eroded out more of Lake Pend Oreille. And when they expanded out into this prairie, the Rathdrum Prairie, they deposited hundreds of feet of flood sediment. Very coarse sand and gravel was deposited out here in this outburst plain. And it actually it raised the level of Rathdrum Prairie out here with hundreds of feet of flood sediment. And the raising of the level of the valley caused the streams that were coming in from the sides to pond up against that buildup of sediment out in the valley. So that's why these lakes are here. These are all lakes that were dammed by flood deposits that were filling the Rathdrum Prairie. So all that water ended up going down through Spokane area. There were some floods when the ice wasn't advanced to its maximum. Some of the floods actually went up through this area and then out through Newport and then into the Little Spokane River and rejoining these floods near the Spokane area. So here's Spokane over here. The floods were coming in from the northeast, and they continued on downstream into the Columbia Valley and the Spokane Valley, which during the Ice Age, there was Lake Missoula that was occupying both the Columbia Valley and Spokane Valley. So the waters from Lake Missoula were coming in, hitting glacial Lake Columbia, and then spilling out across two of these scabland tracts. This is the Cheney-Palouse scabland tract. This is the Telford Crab Creek scabland tract. And some of the floods, especially towards the end of the Ice Age, ended up going down Grand Coulee and carving out Grand Coulee, which is over here. So again, here's glacial Lake Missoula, the ice dam, which when that broke apart, all that water from Lake Missoula drained down. It hit Lake Columbia, which is a couple thousand feet lower than glacial Lake Missoula, and overfilled Lake Columbia very quickly, and then drained out across what we call the channel scabland. But eventually all that water had to go through this one little opening down here called the Little Gap. It was only 2 miles wide. There's twice as much water going in the gap to go through it once, so it backed up, creating a big lake a temporary lake called Lake Lewis that was only there for 2 or 3 weeks, which is how much time it took for all that flood water to drain out through the Columbia Gorge and out to the Pacific Ocean. So before the Ice Age floods, most of Eastern Washington was covered in these beautiful hills of Palouse soil, wind-blown Palouse soil. And when the floods started coming down, then they started running over that Palouse wind-blown soil, and as they eroded down, eventually a lot of times they would erode down completely through that pile of Palouse down to the basalt bedrock that was underneath. So here you can see where the floods eroded the Palouse, left behind remnants of the Palouse, creating these islands, these lighter colored islands, and then eroding down into basalt, carving channels into the basalt bedrock underneath. So the floods were effective at eroding and streamlining these Palouse islands. They're always steeper on the upstream side, they're more gentle on the downstream side, and they're scarped along the outside margins where the floods eroded the margins of these Palouse hills. They left these escarpments. So the next slide I'm going to show you is one Palouse island that was out here, and it's a fairly small one compared to the others, but you'll see in the video that it's actually a pretty good sized island, and this is it. You can see we're going downstream. This is the upstream end of the island. This is the downstream end, and it actually carved a channel going across that island. Here's a few more islands of Palouse that were eroded down in the area of Palouse Falls. So when the floods were flowing through this area, through the Cheney-Palouse tract, they were flowing over the tops of these islands, and they were eroding down into the basalt bedrock underneath. But they left behind these erosional remnants of the Palouse that we can see as streamlined Palouse hills today. Well, here's some classic scabland now. The head of the Cheney-Palouse scabland tract near Sprague Lake, which is up here, near Sprague Lake. The floods did mostly erosion, except in a few places where the current was allowed to slow down, you would get deposition of sand and gravel onto these flood bars. And you can see these flood bars This flood bar actually has some beautiful giant current ripples on it. You can see these parallel lines are places where the floods were depositing sediment onto this bar and creating a wave at the base of the flood flow that was causing the migration of these ripples moving across that flood bar, which preserved these giant current ripples, similar to what we saw up in Lake Missoula. But these were from the downstream end of the floods and not the upstream end. I'll be showing you more of these ripples later on in other places. Rock Creek Coulee is a beautiful canyon that was carved out by the floods at the very western end of the channel, the very eastern end of the channel scabland. You can see this. It's definitely a coulee. It's a horseshoe. It's a box-shaped coulee with steep sides of the walls, flat bottom. Today, Rock Creek Coulee is occupied only by a single very small stream. This is Rock Creek. It's a tiny stream compared to when the floods were coming through. We call this an underfit stream because it's much smaller than it's possible to have actually carved out the coulee. The coulee itself was carved out by these floods. This is looking upstream towards Spokane, which is up here in the distance. This is the Palouse that was preserved. It wasn't eroded along the margins of the coulee. This is kind of the central part of the channel scabland, place along Lake Creek. There's preserved Palouse soil that wasn't eroded by the floods. The floods definitely eroded out the canyon in between. Moses Coulee is over on the west side of this channel scabland. This is the lower coulee. You can see these beautiful hanging valleys. Moses Coulee is just as long and as impressive as Grand Coulee, although it's a little harder to get to. But you can drive into it. There's a public road that goes almost the entire length of the coulee. Some pretty impressive scabland. So looking downstream toward the lower part of the Moses Coulee. The floods were completely filling this valley. And all these canyons, these channels were carved out simultaneously by these huge floods. Okay, so now we've migrated over to the Upper Grand Coulee. This is the Upper Grand Coulee near the Columbia Valley is up here. Grand Coulee Dam is up here. And off to the east side of Upper Grand Coulee are these Castle Rock cataracts, a couple of beautiful horseshoe-shaped canyons or cataracts that were carved out by floods that were spilling over through these channels. And as they did so, they carved recessional cataract canyons. Cataract started over here, but with each flood and duration of flood caused these cataracts, these horseshoe-shaped canyons, to retreat upstream into the direction of the flow of the floodwaters. This is Castle Rock over here. Northrop Canyon State Park is this canyon here. And up here in the upper part of the coulee too, you can actually see where the basalt pinches out against the granite bedrock. Down in Tri-Cities where I live, the basalt's thousands of feet thick, up to 2 miles thick. Up there on the margins of the basalt plateau, the basalt's thin, and here it's only a few hundred feet thick, and underneath is the bedrock, the granite bedrock that's underneath the basalt. This is the over on the opposite side of Grand Coulee, Upper Grand Coulee. This is looking southeast towards Steamboat Rock here. This is the main upper Grand Coulee here, Banks Lake, big body of water that's man-made in the upper part of the coulee. And about halfway down the coulee is Dry Falls. And Dry Falls is multiple cataracts again. These dry waterfalls that are horseshoe shaped. And in between Dry Falls, you have Umatilla Rock that runs down the middle. This is a recurring feature that we see over and over again on the channel Scabland. We see these multiple cataracts, canyons that are separated by a blade of basalt, like Umatilla Rock, shown here. So the water going over, well, the cliffs of Dry Falls. This is a 400-foot high cliff here. So we know the water going over the top of the falls was at least as high as or at least as deep as the cliffs are high. So if you add 400 feet to the top of the cliffs, that would have been the depth of the water up here. So everything in this image would have been underwater, hundreds of feet of water, 400 feet of water, except for the very tops of these hills over here on the sides. So you can start to see some of the grooves that were carved out as the floods were eroding across the top of this basalt plateau up here that carved out these grooves and oftentimes potholes. Intensely scoured, eroded flood surfaces. Here's a pothole here. You see the grooves. This is Dry Falls. There's actually 3 cataracts. There's 1, 2, and then there's the beginning of a 3rd one over here. There's Umatilla Rock. Dry Falls Visitor Center is over here. If you've ever been to Dry Falls, driven via the highway, you've probably stopped there and you've looked out, and mostly what you can see from the visitor center is just this, and you can kind of peek in to see this canyon here, but you can't see that this cataract complex goes for 4.5 miles to the east. It's huge, and it was all inundated at the same time, simultaneously, by the same flood. Deep Lake down here, some beautiful potholes, Deep Lake potholes down below. Here you can see the grooves that are they're aligned parallel to the flow of the water, which is coming from the north up here and flowing towards the viewer in this image. There's some of those potholes closer up on your Deep Lake. Cavernous potholes, 100 feet wide. Sometimes they're as deep as they are wide. If you fell into one, if you survived the fall, you'd probably never be able to climb out because a lot of them are overhanging down below. These are formed by swirling floodwaters, or some people call them colts, swirling eddies within the floodwater, carved out those giant potholes. There's some more scab land down below Dry Falls. Kind of see the grooves, parallel grooves etched into the top of the basalt cataract, recessional cataract here. So here's a feature called the Great Blade, which is pretty neat, one of my favorite features. And most people don't know about it, have never seen it or heard about it because you can't really see it from the ground. You really have to get up in the air. There's a highway that goes down the lower Grand Coulee, and once you're driving down, you can look up and see a wall of basalt over here, which is the Waterville Plateau, and then You can see another wall of basalt over here. You think that's the edge of the canyon, when really there's another valley, another canyon on the other side of what we call the Great Blade. Okay, this is up to 2 miles long, and in places it narrows down to just a few tens of feet wide. It is truly a blade, and it is special. This is the longest blade of any you'll see in the scabland. See, so there those floodwaters moving simultaneously down Lower Grand Coulee. They're also coming down that other side. So here's looking and going up to the top of the blade. The highway, this is Lake Lenore down here. The highway is out of view down here to the right. You can see how narrow this thing gets. The floods flowing on either side actually went over the top. They were probably another couple 100 feet deep over the top of the blade itself. And they created this beautiful scabland downstream. Lake Lenore, it's a beautiful lake along the Lower Grand Coulee. And I should mention here that the Lower Coulee is partially there because there's a thing called the Coulee monocline, which is where the basalt flows were bent over very steeply. They were flat up here, and then they bent over due to tectonic forces, bent these rocks over, and you can see these are remnants of basalt that is dipping down to the east. And then they flatten out again over here on the east side of the coulee. But within the coulee itself, the rocks are bent over, and they were highly fractured in the process of being bent and deformed. They were highly fractured, which allowed the floods to preferentially erode out the coulee along that more fractured zone along the Coulee monocline, which is where Lake Lenore is today. Here's another coulee called Spring Coulee to the east of the Grand Coulee. It's also known as Billy Clap Lake. You see where the floods were coming down, created these couple channels through here. You can see the streamlining of the channels. So big basalt knobs sticking up buttes. There's some giant current ripples along the margin of Spring Coulee. So the floodwaters were filling the coulee, and they are also spilling over onto the margins next to the coulee itself, creating these ripples. So out in the middle of the channel scabland is Coffee Pot Lake. This is within the Telford Crab Creek scabland tract. And Twin Lakes, or another set of lakes. This is occupying Lake Creek Coulee. It drains down near through the Odessa area. See the nice rock benches. These are places where the floods actually eroded these individual lava flows. Okay, this is one lava flow. Here's another one, a third, fourth, fifth. These are places where the floods, as they eroding these coulees, they would erode the margins of the coulee and erode and peel back the lava flows to these benches. So it started out and peeled this flow away, and as another flood came through and it eroded this coulee or this basalt flow back. So we have these tiers of basalt benches that were created by these floods that were peeling away separately these individual separate lava flows. So here's another feature called the Odessa ring craters. These are a little bit harder to describe and explain because it's a fairly complicated process that produce these. But in a nutshell, these rings that we see here were formed when the lava flows came out This particular lava flow came out about 15 million years ago. And when it did, it probably ran over a stream or maybe a small pond or a lake that was sitting on the surface before the lava flow came through. And the lava flow came through, ran over that water body, and as it did, it produced steam, which produced these circular openings in the lava flow. The steam would have caused tremendous pressure uh, uh, of the water underneath the lava, which created these dikes, which allowed lava from the interior of the flow to rise up through the dikes and out onto the surface. And as that lava came to the surface through these dikes, that pushed the center of the system down, which pushed up more lava around through the dikes. And then eventually all that dike that opening would have been filled with lava that was oozed up from down below. And then later the lava was covered with these hills of windblown polluted soil for millions and millions of years. And then it wasn't until in the last million years or so, the floods came through and they eroded away all the topsoil and down into the basalt bedrock. And the floods preferentially eroded out the weaker rock in between the dikes that came up from these ring dikes, these ring craters. And they left behind they etched out the rings that we can see today. So that's a fairly simplified explanation. It probably may not make a lot of sense to people, but that's the best explanation that geologists have come up with so far for these ring dikes. And they're especially prevalent in the Lake Creek Coulee area. We do see them in a few other places, but mainly in the Lake Creek Coulee. This is a little bit north of Odessa. Further downstream in the Cheney Blues Tract is HU Ranch Coulee. It's a very straight canyon that was preferentially eroded out due to tectonic forces that were able to, that were pulling apart or causing the crust to pull apart in this lower end of the Cheney Blues Tract. And as they did so, they created these very long linear tectonic fractures. And when the floods came through, they preferentially found these zones of weakness and preferentially eroded out coulees like HU Ranch Coulee along one of these tectonic fractures, which is here. Streams and floods don't normally go in straight lines like this, but they do when they encounter these weaknesses in the bedrock. Here's another example. Devil's Canyon is another very straight canyon. It's in parallel with HU Ranch Coulee and Palouse Canyon. So Devil's Canyon over near the town of Colotis, just north of the Snake River. There is a road going all the way down that. Again, it's not easy to find unless you know where it is. So now I'm going to focus in on the areas that were filled in and occupied by floods that came into the Quincy Basin. So all the floodwaters from from Grand Coulee came down Grand Coulee, and they were going really fast and furious. They hit Quincy Basin, which is a broad open basin, and then they spread out. That allowed floods to slow down temporarily, caused lots of deposition of sand and gravel within the Ephrata area, Moses Lake area. And then the floods came in so quickly that they actually filled the basin and were able to spill out over the west sides. They were able to climb hundreds of feet up into the valley margins of the Quincy Basin and spill over into Potholes Coulee and Frenchman Coulee. While at the same time, they were draining down through Drumheller channels, which is an area where the floods eroded because they couldn't go over the Frenchman Hills or the Saddle Mountains. Those were too high for the floods to flow over. So the floods actually were restricted to flowing through Drumheller and the Othello channels going to the south, but they also flowed through Potholes Coulee and Frenchman Coulee off to the west at the same time. Here's Drumheller channels. So the floods were coming from the north, from Grand Coulee, coming down to the south. And as they did go through the Drumheller, they carved out this complex network of anastomosing interconnected channels. They left behind islands of streamlined islands of basalt, as you can see here. This is a streamlined island. The floods were flowing from the lower to the upper part of this image. And as they did, they plucked these beautiful columns of basalt around the margins of this basalt island. These are beautiful 50-foot tall individual columns of basalt that are 50 feet tall and several feet wide. This is Crab Creek that occupies. It's the only stream running through. It's an underfit stream that runs through the Drumheller channels today. Columbia River used to flow through there, but not since the Ice Age. So down at the lower end, beyond Drumheller channels, is Othello channels, where the floods flowed around the east end of the Saddle Mountains, carving out this channel complex, similar to Drumheller in the Othello area. You can see the beautiful grooves carved out into the basalt bedrock going through the Othello channels. This is actually mostly on private land, so it's restricted access. That's the beauty of a drone, is you can fly anywhere. So now we're going to switch over. We looked at Drumheller channels, Othello. Now I'm going to switch over to Potholes Coulee and the Frenchman Coulee, which were two dual cataract canyons that spilled over from the west, spilled over into the Columbia River, flowing west. Here's Potholes Coulee. Again, it's a dual cataract canyon. There's one cataract that fills Ancient Lakes Basin, and then there's another cataract that fills the Dusty Lake Basin with a beautiful blade, single blade of basalt running down the middle. And keep in mind, when these coulees formed, they started out, the floods were spilling over out of the Quincy Basin, which is to the right. They were spilling across the basalt surface until they got to the Columbia River, and then they dropped hundreds of feet down into the Columbia River. And that hydraulic gradient was so strong, it allowed the cataract to start forming. So the cataract that you see here started out way down here and way down here. And with each flood, that cataract would progressively recede further and further upstream to where they are today. So in Frenchman Coulee is the same thing. Here's a Frenchman Coulee. It's a little bit bigger, longer coulee separated by a blade, and then Echo Basin, which is to the left or south of the blade over here. There's the Columbia River in the distance. So these cataracts again started out down by the Columbia River, and then with each flood, the cataracts, these waterfalls or this valley. There's the feathers, basalt columns. All right, so switching gears a little bit, we're going to talk a little bit about these giant current ripples out in the scabland. Here's some near Odessa. Down, if you drive west of Odessa, you can actually drive right through these ripples. You wouldn't even know it. You can't even see them from the ground. You really have to get up in the air to see these things. There's some more. Here's Crab Creek coming down near Wilson Creek. Here's 3 sets of ripples on 3 different surfaces. So the floods were coming down and eroding or depositing sediment onto 3 different flood bars, creating these ripples. Here's some more ripples in the West Coulee area. You can actually see the composition of the bar, which is mostly sand and gravel within this borrow pit that's eroded, not eroded, but man-made pit that was excavated into the side of this flood bar with the ripples. Babcock Bench is a pretty special place. And again, most people don't know it, have never been there or seen it. And again, you really have to get up in the air to really appreciate it. You really can't see it from any public roads. You really have to get up in the air and look down onto it. This is what it looks like in a LiDAR image, which is a special remote sensing tool that strips away all the vegetation and down into the underlying bedrock. I mean, you really see the nature of the erosion and the way the floods had their way with the basalt surface. At one time, this was all a single basalt flow filled up to this common elevation. But since that lava flow came out millions of years ago, the floods came through and they've eroded this very complex, very bizarre erosional topography on top of that basalt flow. And this is the Columbia River, again, Crescent Bar here, West Bar over here. Well, I'll show you the giant current ripples of West Bar next, but first we're going to look at, we're going to focus in on Babcock Bench, which is across the river. So you can see the basalt surface comes to a common elevation, but in between we have these places where the floods complexly, savagely eroded the basalt surface. I like this. This almost looks like the piece out of a picture puzzle that was eroded out. And a moat with a moat going around the outside. So the erosional patterns we see are probably related to changes or small changes in the internal structure and resistance and hardness of the basalt flow. Here you can see some basalt, some potholes that were eroded into the basalt. This surface here is 700 feet above the Columbia River. Down below, there's Babcock Bench up here. So across the river is the West Bar. Some of the best examples of giant current ripples anywhere within the Scablands. For a long time, people assumed they were from glacial Lake Missoula, but since studying them in the last dozen or so years, most geologists and investigators think West Bar is situated in the wrong place to be formed from floods from Lake Missoula. It is, though, downstream of where glacial Lake Columbia used to be. And when the Okanagan Lobe blocked the Columbia River, we had this big Lake Columbia. And then at the very end of the Ice Age, the Okanagan Lobe receded, moved northward. And eventually all that water from the Lake Columbia was allowed to drain out in its own flood, similar, but perhaps not as big as a Lake Missoula flood. And it drained down the Columbia River, which would have taken it immediately across West Bar. So we think West Bar was where ripples formed from the last flood of Lake Columbia about 14,000 years ago. Here's a closer up view of those ripples. Again, the orientation of the ripples indicates the floods were moving from the north to the south. And they're asymmetric. In other words, they're a little steeper on the downstream side, which is an indication that these were normal dunes ripples that were moved from those currents. And there might have been some swirling of the floodwaters that produced some of these holes, depressions on the surface of the bar. So further downstream on the Columbia is Sentinel Gap. This is another place where floods were allowed to drain through the Saddle Mountains into the Pasco Basin. This is looking south in the direction of the flow of the water. Here's the Sentinel Gap. This is looking upstream now into towards Sentinel Gap. And you see the boulders that were transported by the floods that were coming through the gap. And most of these are basalt, angular basalt boulders that were probably ripped out of the side of the Sentinel Gap and then deposited as the floods were allowed to expand into the Pasco Basin. Occasionally, you'll see a boulder of granite or argillite or some other exotic rock, which were probably associated with icebergs that were grounded in this area. Okay, so this shows you the extent of Lake Lewis and the Pasco Basin. It goes way up into towards Moses Lake. Here's Sentinel Gap, where we just looked. But during the Ice Age floods, there was twice as much water going in the gap, below the gap, than could get through. So you see the water. There was a hydraulic dam created by the water that backed up, reversed the flow of the Yakima River up to Yakima and beyond, or reversed the flow of the Walla Walla River to Walla Walla and beyond, and reversed the flow of the Snake River all the way up to Lewiston, Idaho, which is up 80 miles upstream. So everything in blue would have been underwater. The darker the blue, the deeper the water, which would have been about 900 feet deep over the Tri-Cities. Our hills south of us, Badger Mountain, Candy Mountain, Red Mountain, those were just islands within Lake Lewis. So here's a view of looking down below the gap, looking downstream. This is Two Sisters, which is a landmark within the below the gap area. Floods were many hundreds of feet deeper than either Two Sisters or this ridge. So this is the Columbia River. It's a backwater from Lake McNary Dam downstream. But during the floods, the floods filled below the gap, which is about a mile wide, but they also went up and over the top of the sides of the gap. You can see this high point here was still 100 feet below the maximum level of the flood. So the floods spilled over for another mile on either side of the gap and carved out channels in the areas above to the margins, along the margins of the gap. There's Two Sisters again. So the floods went all the way up to the top, mostly almost to the break and slope. Here on the west side of Wallula Gap, this point here was still 100 feet below the maximum level of the flood. So the floods were spilling over to the right and then rejoining the Columbia River flows downstream. There's a cross channel, spillover channel. See the places where the flood spilled over the west side. There's a channel through here. As well as going down the main part of the gap, they also spilled over, creating these channels off to the side of the gap. Okay, so now from Alula Gap, the floods headed down, took a bend to the west and started following the Columbia River downstream. Here's the Columbia River down here. Here's I-84, a highway, the freeway that runs along the Oregon side of the gorge. And here's a canyon called Philippi Canyon. And there's a roadside, there's a sign along I-84 saying Philippi Canyon, which will take you onto this road here. It'll take you up into Philippi Canyon if you were so inclined. But from the freeway, you really can't see much. You can see there's a big pile of sand and gravel here. This is a big eddy bar at the mouth of the Philippi Canyon that formed as the floods were coming down from the left. They were racing down the Columbia Gorge, and as they hit the side canyon, there was an eddy that formed along the inside, the upstream side of this canyon, and that deposited this bar that's up to 300 feet thick along the inside of Philippi Canyon. And then the floods rose up to the very top of the ridge, you can see here, in order to spill over into the channel complex behind it. And then eventually they drained into the John Day River, which is behind here. And you can actually see part of the John Day River up here, which drains down to the right over here. So the floodwaters that were coming down the gorge had to have been moving extremely fast, extremely quickly in order to fill this canyon and allow it to drain down the John Day River before floods downstream could backfill up into the John Day River. So this is all evidence that Brett's used for the floods coming in very quickly, very suddenly. So this is all scabland for here. These are channels of basalt erosion and channels, potholes, cataracts, rock benches eroded. Typical scabland topography eroded. As the floods came in from the Columbia this way, they swept, they eroded through here, and then they dropped into the John Day River, which is downstream. Here's that flood bar again I was telling you on the inside and the upstream side of Philippi Canyon. This is all sand and gravel, 300-foot high flood bar, now covered with sagebrush. And there's the bar down there, which is quite a bit lower than the high water for the floods. The floods had to have spilled through here, carved out these channels into the basalt canyon, carved out. So this is typical scabland erosion, similar to what you'd see up north, but yet it's in the gorge. Here's the Maryhill Museum. Here's the Maryhill bench. Floods flowing down that came across Maryhill, where the museum is today, were probably 300 or 400 feet deep at Maryhill, which was another few hundred feet higher than the river down below. So hundreds of feet deep, 800 feet deep, maybe floodwaters flowing down through the gorge. So here's the bench the Maryhill sits on. So that was about halfway up the floods. The floods went up another couple of 300 or 400 feet above this bench, way up into the hillside. And you can see that based on where you see erosion along the gaps of the gorge. So you see here, there's erosion, there's planed off rock benches and sediment benches going up to this point. So the floods in this area called the Celilo Scabland, floods went up to this height and they eroded everything else below it. Down here you can see the extreme erosion going on this plateau. I-84 again, way down here. As you're driving down 84, you can't see any of this because it's all hundreds of feet above you. You see this rock wall that you're driving along, but you think that's the edge of the valley, but it's not. The floods went up and over the top of that and eroded all the way up to about this point. Some potholes, nice potholes carved out. These are tectonic fractures again. These linear features are places where the floods preferentially eroded out along these planes of weakness, these tectonic fractures. Rock benches, beautiful rock benches. These are multiple lava flows that were peeled back by the flood erosion. Like peeled back like layers of an onion. Okay, downstream of, just downstream of Celilo is Fairbanks Gap. Okay, this is a place where the floods coming down from the upper coulee, the upper gorge, going west. This is Mount Hood in the background, flowing downstream. They actually were able to. They were so deep they actually ran deep enough to rise up against this ridge and spill over in order to carve this bench or to carve this gap that you can see through here. And when they did, when those these must have been some of the biggest floods going down the gorge, when they spilled over and carved that gap, they went down as far as the basalt and then they stopped. Okay, this is sedimentary material that's easier to erode. But when the floods eroded down to the basalt, then that's as deep as they eroded. But they eroded easily through that sedimentary material up above, but still left behind a gap. So that tells us how deep the water must have gotten in order to create this gap that we see here. Okay, so there's a closer up view of the gap. Here's the basalt surface is right here. You can see the floods were able to erode down to the basalt, but not much below that. And that was one of the few places where the floods could actually get through. There must have been a slightly lower area right at the top of the ridge to allow the floods to spill through here. But once they started, there was nothing to stop them from eroding all the way down to basalt. There's a hanging channel that's hundreds of feet up above the river that was carved out by these floods. It's going through Fairbanks Gap. Okay, further downstream is a place called Horse Thief Butte State Park. This is the highway on the Washington side that goes through Horse Thief Butte. See, here's a basalt flow. It's got a kind of a spindly, characteristically spindly top. There's this, you can see there's a groove cut through here, and that's probably one of these tectonic fractures that was preferentially eroded out. There's a groove. There's another one. They're all parallel with each other, which are an indication they all form simultaneously from these tectonic forces. And then floods came through, and they took advantage of these planes of weakness, preferentially eroding channels through them. This is our Rowena Gap. Keep that in mind. This is the city of the Dalles. Downstream, Rowena Gap is over here, Mount Hood. There's the Port of Dalles out here. This is all scabland. Scabland topography. There's Horse Thief Butte. So you can park down here, and there's some nice hikes that go up into this area. You can even hike up to the top of Horse Thief Butte. It's popular with rock climbers. So you can really see here how deep the floods got. This area up here was, you can see there's no basalt exposed up here. It's covered over with a covering of soil, slope wash mostly, until you get down to here, and then you can start to see the basalt is exposed. And that's where the floods, that's the maximum level of the floods, was somewhere up here, which was hundreds of feet above where the river is today. And near the town of the Dalles is the strand lines. See these parallel lines, horizontal lines, are places where the floods came through and deposited some sediment. And as they did, they were able to erode. Small later floods were smaller, which is supported by the fact that these you see preserved trend lines or strand lines going down this sedimentary deposit. The fact that these higher strand lines are from the earlier floods, and then as the floods got smaller, they left behind similar lines, parallel lines that were further down, lower on the bar. You can actually see these from the freeway, from I-84, if you look over near Rowena Gap. You can actually see those strand lines. There they are again. So this is Rowena Gap. It's a narrow opening in the basalt. It's actually where a geologic structure, an incline, crosses over across the river. It narrowed the gorge such that it was also another gap, hydraulic constriction for the flood. So the floods coming down from Wallula Gap, when they encountered Rowena Gap here, they were actually temporarily able to back up behind it from another lake called Lake Condon, which was about 1,000 or 1,100 feet deep, or was 1,100 feet elevation. So just below Rowena Gap is Rowena Dells in the town of Rowena. Freeway is down here, and this is Rowena Gap. You can see how it narrows down. That was another hydraulic constriction for the floods. But they ripped through Rowena Gap and then they spread out into the Rowena Dells, which you can see here. These are the Rowena, you can see the canyons, hints of cataracts that were eroded into the basalt. This is looking north across the Rowena Dells. There's Mount Adams in Washington. This is kind of a cataract that was carved out. Potholes on this rock bench above the cataract. And it's beautiful wildflowers this time of year, and on balsam root, lupin, they're especially pretty this time of year. Popular hiking trails. There's a hiking trail going out onto this bench to go past these potholes. So these are Mima mounds. These are post-flood deposits of soil that were laid down maybe due to frost action or some other, animal burrowing or something was deposited these surfaces. But those are unrelated to the floods. The floods would have wiped those things out. So we think they're post-flood evidence of pattern brown. And so this is looking downstream, Columbia River. So down further is Beacon Rock State Park. It's a volcanic plug that's around, I think it's around 55,000 years old, probably related to volcanism of Cascades. in the early Cascade time. It's not basalt, but it's a plug of stuff that the basalts flowed around. And since then, the river and the floods have eroded away and left behind this erosional remnant of the volcanic plug. When the floods came through, they were they were up near the top of this beacon rock. They didn't actually go to the top, but they went up somewhere near the top, maybe a few dozen feet within the top. We had the floods, so this valley was pretty much filled with flood water going up to at least this point. There is a trail going up there. It's a wonderful trail. It's a lot of switchbacks. You can see people hiking up. There's dozens of switchbacks going up there, but they do go all the way up to the very top. The trail is, and there's good rails, good handrails going up, so it's safe. Pretty popular. It's a state park down here. It's not that far. It's about a mile maybe altogether to get up to the top, but it's quite an elevation. Okay, so now let's see. We're gonna wrap up. Talk about the floods that came down the gorge from the right. This is the gorge, and then when they hit the Portland, Vancouver basin, they spread out. Floodwaters spread out, caused lots of deposition of flood deposits in the Portland and Vancouver basin. And a lot of that floodwater came in so rapidly, it backed up behind a hydraulic constriction up here at Kalama, called the Kalama Gap. And that allowed floodwaters to back up to an elevation of 400 feet behind Kalama Gap. And that would have forced floodwaters to drain south here through Oregon City, as well as through Lake Oswego. So these are two places where the floods backed up out of the Portland Basin and drained south into the Willamette Valley, all the way down to the city of Eugene. We had waters backed up to 400 feet deep, called a temporary lake called Lake Allison. It was probably only there for maybe 2 or 3 weeks at the most. But within this area, I'd like to talk about the ice rafted erratics. There's some special erratics that were deposited in this area, and I'm going to talk about those to finish up this talk. So first of all is the Bellevue erratic. We talked about this earlier. I showed you a drone video showing you where we flew over this beautiful piece of argillite that now is part of a state park that you can hike up to. But originally it originated somewhere up probably in northern Idaho, and from belt rock that was being ground away by ice from the ice dam for Lake Missoula. So the ice grinding along the sides of the Clark Fork River Valley picked up pieces of this argillite, or they fell onto the ice when were entombed within the ice. And the ice dam broke up from the Lake Missoula flood, and eventually a lot of those icebergs ended up down here in places like the Willamette Valley, including this beautiful piece of argillite at the Bellevue erratic. But there's also even a more unusual erratic, and that's what's referred to as the Willamette erratic. It was found back in the early 1900s, over 100 years ago. There were some people up who lived in the Portland area. This is the Portland Basin up here, so southwest of Portland, near the town of Willamette. They found this meteorite sitting on the surface up at an elevation of 400 feet. That coincidentally, or maybe not coincidentally, is the same elevation as the highest watermark for the Ice Age floods. We know the floods went up to 400 feet based on other erratics that we've seen in the Portland Basin and the Willamette Valley. So we think that this Willamette meteorite was probably fell into the ice sheet, maybe up in Canada, was carried down over the eons down into northern Idaho, with the Cordilleran ice sheet became part of the ice dam for Lake Missoula, and then during one of the Missoula floods, it was carried down. But probably during one of the largest floods, it was carried down with the ice because it is at the near the high water mark for the floods. So, and also there are other erratics nearby. People that found the erratic originally reported other exotic rocks like granite and other unusual rocks other than basalt associated with the erratic. So there's a good chance it was part of an iceberg carrying other erratics with it when it was carried down in an iceberg. So today we know it was a pitted iron nickel meteorite discovered in 1902. Today and since the early 1900s, it's been in a museum in New York City, and you can still anybody can go to see it in New York if you're ever there. And it's one of the largest. It is the largest found in the U.S. and one of the largest ever found in the world. So that's the end of my talk. I've gone on longer than I should have, but thank you for staying with me. I would like to let you know that a lot of the videos that I showed you today are posted online on. I have a YouTube channel called Age Floodscapes. So if you want to go back and see any of the videos, in addition to lots of others I've posted, 30 so far online, I'm adding new videos periodically. And if you subscribe online, you can actually get notified as I post new videos, like similar to the ones I showed today.
All right.
And I do have a couple guidebooks that are available now, and also a new book that just came out in the last few weeks, Ice Age Floodscapes of the Pacific Northwest. This is a hardcover coffee table type book with over 300 color images and 180 pages. So you can order it either at Springer.com, at Amazon.com if interested. So with that, I'm gonna stop my share.